Hi, I'm Ed Stanek. I'm a professor of biostatistics at UMass Amherst in the School of Public Health. And I'd like to talk with you about predicting low dose effects in high throughput studies. There are many studies that have been conducted, routine studies that are screening for chemicals, usually to look for LD50 levels, that have a relatively limited dose range, maybe 5 doses, and with the target being actually the LD50. These studies offer a very large volume of data that potentially could be harvested to try to look at whether or not the response in the low dose range is actually elevated, or like a threshold model might predict, or actually below the control response. So what our talk is about is issues that relate to that. There are two perspectives, and I think these perspectives really are statistical perspectives. And the point of the talk, our point really is that a second perspective, the one based on estimation, is really more appropriate when you're looking at data in the low dose range. Typically, when people approach such studies, it's from a hypothesis testing basis. What dose actually is developing a LD50 level, something like that. But in these studies, if we can identify the areas where the doses that are actually below some threshold, where they are low doses, then we can quantify that, and that's the point. The example that we've illustrated is one from the National Cancer Institute, where they have yeast data, and they have in 96 well plates done bioassays on over 2,000 chemicals in 13 different strains of yeast. The first step in the process of trying to look at low dose responses is to identify experiments where there actually are doses below some benchmark dose. And we chose a benchmark dose at 95%. That had to be bounded by responses for 2 adjacent doses, and there had to be a toxic dose, which we defined as having a dose less than 80%. This identified a number of chemicals where actually there were eligible doses in this low dose range below the BMD5. Among those, one approach would be to test the hypothesis. Is the average response above control? And that results of that hypothesis tend to lead to failing to reject the null hypothesis. For example, among wild type yeast strains, there were 253 chemicals that had 3 doses below the BMD5. In testing individual tests as to whether or not there was a difference between the control and the average response in the low dose range, only 30 of the 253 hypotheses were rejected. And in fact, if you'd control for multiple comparisons, only 4 would have been rejected. So some people may claim that there is nothing to be gained by looking at these high throughput studies to evaluate low doses. But if you take a different perspective on this and you say, let's just see what we can do in terms of estimating the magnitude of the response in the low dose range, then it's fairly simple to construct means in the low dose range for each of these 253 chemicals. Tabulating those means gives a clear demonstration of responses that appear to be above the control response. Adding confidence intervals to that provides some more information about what the distribution of responses actually is. And these can be tabulated in a cumulative manner so that you can have a comparison, a general comparison of the distribution of average response at these low doses. To add more clarity to this picture, a background measure can be added that will give an idea of how, for the control responses by themselves, how much bounce you might actually expect. And so the comparison then of the actual observed data in the low dose range with this background gives you a sense of whether the data tend to support a hypothesis where responses are elevated, where they're roughly the same as the threshold responses, or whether they're actually below the control responses. A refinement can be made on this, and that's the last point that we make. It's possible to introduce chemicals as random effects. This is a very mild assumption. It corresponds to assuming that the chemicals resulted from a sample of some larger set of chemicals, which may be a reasonable way of thinking of the problem. The advantage of doing this is then, rather than having simply the mean to estimate the response in the low dose range, we can use best linear unbiased predictors. The best linear unbiased predictors reduce they increase the accuracy of the prediction. And actually, we believe that those are actually the best thing to use. So in conclusion, we think that the statistical paradigms actually are different when looking at low dose effects in the context of high throughput studies. The paradigm that I think is most appropriate in these cases is the one for estimation, and by simply estimating the effects in a low dose range, I think there's much to be learned about these studies.